Understanding hardware specifications and performance. 1. Introduction to digital systems. Digital systems are electronic devices that process, store, and transmit information. They include computers, smartphones, tablets, and embedded systems like smart home devices. Every digital system consists of hardware, physical components, and software, programs, and applications that run on the hardware. To perform tasks efficiently, digital systems rely on hardware specifications. Understanding these specifications helps users choose the best device for specific workloads. 2. Hardware specifications and their impact on performance. Hardware components determine how fast, efficient, and capable a digital system is. The key components that affect performance include the CPU, RAM, storage, GPU, and motherboard. Central Processing Unit, CPU, the brain of the computer. The CPU processor is responsible for executing instructions and performing calculations. Key factors affecting CPU performance. Clock speed, gigahertz measured in gigahertz. This determines how fast a processor executes tasks. Higher gigahertz generally means a faster CPU. Number of cores. Modern CPUs have multiple cores, e.g., dual-core, quad-core, octa-core. More cores allow the CPU to handle multiple tasks, multitasking, efficiently. Cache memory, a small, fast memory within the CPU that stores frequently used data. Larger caches improve performance. Architecture and manufacturing process. Newer CPUs are more power efficient and perform better due to advanced design. Pushpin example, a quad-core, 3.5 GHz CPU performs better than a dual-core, 2.0 GHz CPU for multitasking and demanding applications like video editing. Random access memory, RAM, temporary storage for quick access. RAM is the temporary memory that stores data and instructions while a program is running. More RAM allows the computer to handle more tasks simultaneously without slowing down. Key factors affecting RAM performance. Capacity, GB measured in gigabytes, GB, common sizes are 4 GB, 8 GB, 16 GB, and 32 GB. More RAM is beneficial for gaming, video editing, and running multiple applications. Speed, megahertz. Higher megahertz, RAM can transfer data faster, improving performance. DDR versions, newer RAM types, DDR3, DDR4, DDR5, offer better speed and efficiency. Pushpin example, 16 GB DDR4 RAM at 3200 MHz performs better than 8 GB DDR3 RAM at 1600 MHz for heavy applications like gaming or programming. Storage devices. Permanent data storage. Storage devices hold the operating system, applications, and user data. The two main types are hard disk drives, HDDs, and solid-state drives, SSDs. HDD, hard disk drive. Uses spinning disks to read or write data. Slower than SSDs but cheaper and available in larger capacities. Best for bulk storage, e.g., media files, backups. SSD, solid-state drive. Uses flash memory, no moving parts, making it much faster than HDDs. Faster boot times, quicker file access, and lower power consumption. Best for faster system performance, gaming, and professional workloads. Pushpin example, a 512 GB SSD is much faster than a 1 TB HDD, but the HDD has more storage capacity. A combination of both is ideal for performance and storage needs. Graphics Processing Unit, GPU, handles visual and graphical tasks. The GPU is responsible for rendering images, videos, and animations. Essential for gaming, video editing, 3D rendering, and AI processing. Types of GPUs. Integrated GPU, built into the CPU, e.g., Intel UHD graphics, AMD Radeon Vega. Suitable for basic tasks like web browsing and document editing. Dedicated GPU, a separate graphics card, e.g., NVIDIA GeForce RTX, AMD Radeon RX. Ideal for high-performance tasks like gaming and professional design work. Pushpin example, a NVIDIA RTX 4060 GPU provides better performance for gaming and video editing than an Intel integrated graphics GPU. Motherboard, the communication hub. The motherboard connects all components, allowing them to communicate. Important specifications include Chipset determines compatibility with CPUs and IM. Ports and expansion slots, more USB, HDMI, and PCIe slots allow for better connectivity and upgrades. Bus speed affects how fast data moves between components. Pushpin example, a high-end gaming motherboard supports faster RAM and more expansion slots for additional hardware upgrades. 3. Selecting hardware for specific tasks. The right hardware depends on the task requirements. Below are recommended specifications for different use cases. Task. Recommended hardware. Basic use, web browsing, office work. Dual-core CPU, 8GB RAM, 256GB SSD, integrated GPU. Gaming. Quad-core plus CPU, 16GB RAM, 512GB SSD, dedicated GPU. Video editing and 3D rendering. Octa-core CPU, 32GB RAM, 1TB SSD, high-end dedicated GPU. AI and machine learning. Multi-core CPU, 64GB plus RAM, high-end GPU, e.g., NVIDIA RTX 4090. Pushpin example, a student who needs a laptop for basic schoolwork does not need a high-end GPU, but a video editor will benefit from a powerful CPU and GPU combination. 4. Power consumption and efficiency considerations. Higher performance hardware consumes more power, leading to higher electricity costs and heat generation. Laptop versus desktop. Laptops are optimized for battery life and efficiency. Desktops offer better performance but use more power. Eco-friendly choices. Energy-efficient CPUs and GPUs, e.g., Intel E-series processors. SSDs consume less power than HDDs. Pushpin example, a MacBook Air with an M2 chip lasts over 15 hours on battery, while a high-performance gaming PC requires constant power and generates more heat. Summary of key takeaways. White heavy checkmark CPU speed and core count impact multitasking and processing power. White heavy checkmark more RAM allows better multitasking and smooth performance. White heavy checkmark SSDs are faster than HDDs and improve system responsiveness. White heavy checkmark dedicated GPUs are necessary for gaming, editing, and AI tasks. White heavy checkmark choosing the right hardware depends on the task requirements.